So Kristin Isaacs, our third and final speaker on this panel, is a research physical scientist with US EPA at the National Exposure Research Laboratory, which is part of the Office of Research and Development. And she works on computational approaches to predicting, as opposed to measuring, like our last two speakers, population exposures to chemicals and other pollutants. And she's leading an effort called ExpoCast at EPA. And so you'll be hearing more about that from her. And the idea is basically to develop models and databases to forecast the exposure of the population to chemicals that we may not know a whole lot about in other respects. And so a completely different way of talking about and thinking about this issue. And you'll pull up her slides. So let's welcome Dr. Kristin Isaacs.
Okay, thank you so much for inviting me to talk. And as Dr. Solomon said, that I am with the National Exposure Research Lab of US EPA in the Office of Research and Development, and I co-lead the ExpoCast project, where we're really interested in exposure and forecasting exposures for thousands of chemicals, and then using that information to try to prioritize which chemicals we need to look at more closely, either from an exposure assessment standpoint or from a toxicological assessment standpoint. And so today I'm going to talk about some of the modeling tools and databases that we've been building in our project that could really also be used in the alternatives assessment realm to start to look at evaluating both migration, exposure, and even identifying potential alternatives. And because I'm from EPA, I have to say this disclaimer that the views expressed here are only mine and don't represent the agency. So EPA has a mandate to evaluate tens of thousands of chemicals in commerce. And so I think the current number of chemicals that are in the TSCA inventory is something like 84,000 chemicals. So many of those chemicals haven't even been looked at or tested in any real detail. An example is EPA's endocrine disruptor screening program chemical list, which includes about 10,000 chemicals, things like fragrances, pesticide actives, safe drinking water chemicals. And out of that 10,300, only about between 100 and 200 chemicals have been tested or are currently being tested. So how do we start to prioritize these thousands of chemicals and think about which ones we're going to look at first in light of the resources that would be required to do high-tier testing? So there is some good news. So in the past decade or so, there's been this increase in the realm of new next-generation high-throughput hazard testing. And there are several different programs that are that EPA is involved in. There's a cross-agency consortium, the TOX 21 consortium, and the EPA ToxCast program. And these programs are looking at using high-throughput in vitro assays in a dose-response manner to start to identify chemicals that are interacting with biological pathways. And so ToxCast is looking at about 10,000 chemicals, TOX 21 is looking at 10,000 chemicals, and then ToxCast is looking at a smaller set of chemicals but a larger number of assay endpoints. So once you have this kind of high-throughput hazard information, how do you really provide that real-world context and any kind of risk-based context? So that's what ExpoCast is all about. So we are trying to consider multiple exposure pathways, all the things that we've heard about in other, some of the earlier talks where you get exposed to chemicals not only through food, but also, which is what we're focused on today, but also through consumer products, through outgassing from durable goods or household articles, things like SVOCs, outgassing from consumer articles. And then you also have chemicals that you're exposed to from far-field sources. So these are end of pipes, things coming out of industrial applications at the end of a pipe or end of a stack. And so we are building high-throughput methods for all these multiple pathways and then trying to bring them together. And once you do that, then you can compare these what we call aggregate exposure estimates to information that's coming from the high-throughput hazard screening. So this is an example of a chemical where you know something about the bioactive dose that might be associated with bioactivity, and there's always some uncertainty. But it's still, then when you have for the same chemical, you have an exposure distribution, there's still several orders of magnitude apart. So this is a less interesting chemical in the context of a risk-based prioritization. But then you have other chemicals where these things start to overlap, and they can overlap both because the means or medians of these distributions are coming closer, or because you have wider uncertainties in particular pathways. And so that's a more interesting chemical. And then, of course, the chemicals here are what we can consider a high, when you have overlaps like this is a high priority chemical. So, this is maybe one of, if a chemical that looks like this is one of the top 50 chemicals that we would identify using these methods for further testing, like in vivo testing. So we have, like I said, we have different models that cover these different pathways. And how do we bring them all together in some way to forecast exposures for different chemicals? And so there's actually a very, very timely analogy I can use. So many people in the room might be familiar with Nate Silver's 538 blog and his polls plus forecast, where he looks at the performance of polls, many polls over the last several years or last several election cycles, and say, well, how well did these polls perform in the past, and how can I then calibrate those polls and look at their biases and use that to predict the potential, build a model to predict an outcome of a future election. And that's exactly what we do here. And we call that the systematic empirical evaluation of models framework. And so in our case, our elections, or our polls rather, are our exposure forecasts. So you have some polls that only cover state elections, some polls that are at a state level, and some polls that are national polls. Well, we have some chemicals that consider consumer product pathways and some that cover food pathways. And then what we do, our previous elections that we're comparing against are how well these models do for a set of chemicals for which we have biomarker data. So you take NHANES and we get some inferences of the actual exposures that we see for these chemicals. And then we calibrate our models and then use that to forecast exposures for chemicals for which we have predictions or polls, but we don't have past data. Okay, and that allows you to both look at the predictive power of each of the models, but also then account for their biases and come up with a consensus forecast. Okay, so that's kind of the overview of what our project does. And here I'm going to focus on some of the activities that are going on in our project that it would be most relevant to the topics that we're discussing today. So the first thing I'm going to talk about is building high-throughput models of population exposure for food contact substances. In doing that, we have to build empirical models for predicting migration of chemicals from food contact material substances for thousands of chemicals. And so we're going to talk about how we do that. And then something that we haven't really touched on here yet today, but I think would be of interest, is we are also building models and methods for screening large libraries of chemicals for functional substitutes. So we heard a lot about function this morning in terms of the function of a particular product or a particular coating. Now we're going to be talking about chemical function. So what functional role is that chemical playing in a particular food contact substance? Is it a indirect food additive? Is it a slip a UV absorber? Is it a plasticizer? And how can we start to use our predictive models to start to screen huge numbers of chemicals or chemical structures to identify potential substitutes? Okay. So talking about the high-throughput predictions of exposure from food contact pathways. So exposure is really simply, and we heard this in Dr. Cooper's talk and Dr. Bradley's talk, it's just food concentration by food consumption. But how do you implement that in a way that's going to consider thousands of chemicals, or be applicable to thousands of chemicals, even when we're talking about a more high uncertainty, high throughput method? So for example, we identified just from the USDA's inventory of effective food contact substance notifications and their database of indirect food additives. And then we also looked at some of the European data sources that Dr. Bradley mentioned. We identified 1,659 chemicals that are intentionally added either indirectly or directly to food contact substances. So that's not even considering things that are there because they're contaminants. So how do we approach generating migration for chemicals from different properties? And again, the earlier speakers really teed this up nicely. So we have chemicals with different properties. We have foods with different nature and different properties. We have packages with different configurations. So how would you go about building a model that you could apply to these thousands of chemicals? And what we decided to do is build a data-driven empirical model. And again, it's high uncertainty, but it's minimally parameterized and applicable to many chemicals. Okay, so what we did is we used an existing database of FDA migration measurements. And I'm not sure the difference between this database and the one that Dr. Cooper mentioned, but this is available by request from the Department of Food Contact Notifications. And what we did is we went and we said we want to build a conservative model. So we took these migration tests and we pulled out the maximal migration over the period, a steady state migration level over the period of the test. So this is the maximal, what we would consider or assume to be the maximal migration that would occur during the shelf life of the food. And when we filtered the data set, we had about 50 chemicals and about 1,200 observations under different food properties, storage, temperature conditions. And what we did then is build a set of predictors that we could use to build a model. And that included the same types of food categories we heard about earlier: alcoholic, aqueous, acidic, dry, fatty foods, temperature, and then of course we brought chemical properties and predicted or measured chemical properties into this as well. And then a key parameter is actually what is the initial concentration of the migrant in the material that was tested. And I should say that this database included both foods and food simulants. And so we built a linear regression model for migration level, and we used an algorithm called the least absolute shrinkage and selection algorithm that basically identifies the best subset of parameters so you don't have an overfitted model. And so what we were able to do is build a model that captured about 60% of the variance across chemicals and migration. And again, this is very highly uncertain, but we have methods. Our framework can bring in these different this uncertainty into our predictions. And so I'm running out of time, so I'll be speeding through this. But basically, we see that the initial concentration, vapor pressures, and temperatures, and fatty food type are very, very important. And so that's consistent with what we know about migration, other migration testing. And so once we had, I'm going to kind of speed over this, but once we knew migration, then we can make some estimates of food concentrations for these 1,600 chemicals. And we did that by looking at a range of food groups, combinations of food type and storage temperature, frozen, chilled, or room temperature. And then we compared that with some, and then in order to assign the initial concentrations, then we had to say something about chemical functions. So we took the database and we broke the database up into whether it was a plasticizer or a UV absorber, or different types of functions, and got some distributions of the initial functions and applied those to our test data set because we did have information about function from the test data set as well. And then compared that to some literature data. And it turns out for plasticizers, our initial concentrations were very, very high. And so we do see that we are overestimating for plasticizers, but there's probably a reason for that. And then recall that these concentrations on the far, the model predictions are the boxes on the far right-hand side, and these are maximum. So these are the maximal that you would expect. And you do see that for monomers and other indirect food additives, we're doing a little bit better job than we are for plasticizers. But we're currently refining these data as well. So we have migration, and we have concentration, and now we have exposure. So we use existing databases of food consumption information, which is NHANES. So NHANES has 2-day food diaries where they have 7,000 different food codes. And what we did is I had a postdoc who was very patient, who went and actually took these 7,000 food codes and sorted them into the different food groups. Are they fatty? Is it aqueous? Is it stored in the refrigerator? Is it stored in the freezer? And by doing that, we would able to take our migration and our concentration measurements and multiply them by the consumption for each person in those different food categories and get estimates of exposure. And like I said earlier, so when we talk about model evaluation, we compare it with some data. And so we compared our exposure predictions to exposures that were inferred from NHANES biomarker. And the main thing I just want to point out here is that these are all the chemicals in NHANES that we identified as having a food contact pathway. In general, they are much higher than chemicals that only had consumer product pathways. And so we do have overestimates here, and there are reasons for that. We're looking at maximal exposure, and we also assumed that we don't have any information about whether or not a particular chemical, what fraction of food packaging this chemical is in. So we assume it's in 100%, and so that's why you see this. So they were overestimated, but they were correlated. And so I talked about the forecasting scheme framework. This is kind of an initial mini version of that. So this is combining data from consumer product exposures and food contact exposures, and looking at the medians, we are able to build a nice forecasting model that predicts the NHANES median population exposures. So now I think I just have a few minutes, but I just wanted to talk a little bit about chemical function. When we're talking about exposure at large, chemicals, how we come into contact with chemicals is a function of how chemicals are used. And so we've been building in our project a lot of databases of how chemicals are used. How are they used in consumer products? How are they used in industrial processes? Which sectors are they used in? And one thing we're focusing on is functional use. So we went out to a bunch of publicly available databases, retailers and manufacturing government sites, that talk about how chemicals are being used. And we built this database of about 14,000 chemicals with over 200 different functions. And then we have this database, and then we can actually do some modeling. So what we did is we used what's called machine learning-based random forest modeling to take all the chemicals that are in this database, and we developed chemical structure and property descriptors, which can be thought of as chemical fingerprints. And then we took what we knew about how they were used, and we could build predictor models. So you have chemicals that are, let's say it's a catalyst. Well, based on the fingerprints of chemicals that were catalysts, you can build a yes-no model that gives you a probability of whether a new chemical fits into that profile. Does it look like what we know about chemicals that are catalysts? And so we were able to build about 49 models, good models, and I did just want to point out that we did have good models for monomers, cross-linkers, UV absorbers, and plasticizers, food contact, relevant chemicals. And what we can do then is screen large libraries of chemicals for potential functional substitutes. And so we did that. This is the Tox 21 chemicals, because these are ones we had readily available structural data. And then you could also start to, and so the green ones here are where you had a high probability of a certain function, right? And then you could also start to bring in hazard information. So we call these functional substitutes, but maybe they have a much higher bioactivity, so they're not really substitutes, but we could identify when we bring in ToxCast data, bring in the bioactivity, high-throughput screening data, we can start to identify the green ones in here, which are below some threshold of bioactivity. And so we call those candidate alternatives. And again, these are screening methods. So you would want to identify a large list that you would then go and do further testing or further exposure assessment to evaluate. And then I just want to say, oh yeah, big deal. We looked at 6,000 chemicals here. But I just wanted to point out at EPA, we have a really, really great world-class group at the National Center for Computational Toxicology that's building a new source of curated high-throughput chemical information. And this database right now, where they have chemical property predictions and new curated structural information, this database has over 720,000 chemicals. So in the very near future, we'll be able to apply our models to hundreds of thousands of chemicals and identify potential chemical structures that would be ideal functional alternatives. Okay, and then since I'm out of time, I just want to say that we're really focused in our project on screening and prioritization, but we really think that we're building a lot of tools and data sets that could inform alternatives evaluation. So thank you.